What if the very fabric of the universe began with a single, unimaginable leap? A leap so small, so fleeting, that it defies everything we think we know about time, space, and reality itself. This is the mystery of quantum tunneling, a phenomenon so strange it feels like science fiction, yet it's the cornerstone of some of the most groundbreaking theories about the origins of our universe. Today, we're diving deep into 30 mind-bending theories that explore the universe's first quantum tunneling event. From the birth of the cosmos to the possibility of parallel realities, these ideas will challenge everything you thought you knew about existence. Why does quantum tunneling matter? Because it's not just a quirk of physics, it's the key to understanding how something as vast and complex as the universe could emerge from nothingness. So, if you've ever wondered how it all began, or if there's more to reality than meets the eye, you're in the right place. By the end of this video, you'll have a front row seat to the most fascinating ideas in cosmology, and you might just walk away with a whole new perspective on the universe. Ready to explore the unknown? Let's begin. Now, let's step into the very first theory, one that takes us back to the very beginning of everything. Picture this: the universe in its earliest moments was a seething, chaotic sea of energy. But within that chaos, something extraordinary happened. Quantum fluctuations, tiny, random ripples in the fabric of reality, began to emerge. These fluctuations weren't just random noise, they were the seeds of creation. Here's where it gets fascinating. During the Big Bang, the energy density of the universe was unimaginably high. In this extreme environment, even the tiniest quantum fluctuations could trigger something called quantum tunneling. Think of it like this: imagine a ball rolling up a hill. Normally, it wouldn't have enough energy to reach the top, but in the quantum world, there's a chance, however small, that the ball could suddenly appear on the other side of the hill, as if it had tunneled through. That's quantum tunneling. Now, apply this to the early universe. Those quantum fluctuations could have caused pockets of energy to tunnel through barriers that would otherwise seem impossible to cross. This tunneling could have led to the formation of the first structures in the universe, tiny ripples that eventually grew into galaxies, stars, and everything we see today. But what made this possible? It all comes down to the vacuum state, the lowest possible energy state in quantum mechanics. In the early universe, the vacuum wasn't empty, it was a bubbling, energetic soup. And within that soup, quantum tunneling could occur, allowing energy to shift and rearrange itself in ways that set the stage for the universe's expansion. So, in a sense, the Big Bang wasn't just an explosion, it was a quantum event driven by fluctuations and tunneling that gave birth to the cosmos and those tiny ripples. They're still with us today, etched into the fabric of the universe, waiting to be discovered. This theory doesn't just explain how the universe began, it shows us how the smallest, most fleeting events can have the most profound consequences. And as we'll see, this is just the beginning of the story. Now, let's take a step beyond our universe and into the realm of the multiverse. Imagine for a moment that the first quantum tunneling event wasn't just a spark that ignited our universe, it was a bridge, a cosmic doorway connecting us to other realities. This is the heart of the multiverse connection theory, and it's as mind-bending as it sounds. Here's how it works. Quantum tunneling, as we've seen, allows particles or energy to bypass barriers that would normally be impossible to cross. But what if, in the earliest moments of existence, this tunneling didn't just happen within our universe? What if it created a link between our universe and others? This idea ties directly into the multiverse hypothesis, which suggests that our universe is just one of countless others, each with its own unique set of physical laws and constants. Think of it like this: imagine a vast ocean with each wave representing a separate universe. Quantum tunneling could be the ripple that connects these waves, allowing energy or information to flow between them. In this scenario, the first quantum tunneling event wasn't just the birth of our universe, it was the moment our reality became intertwined with others. But why does this matter? For one, it could explain some of the mysteries of our universe. For example, why do the fundamental constants of nature, like the speed of light or the strength of gravity, seem so finely tuned to allow life to exist? If our universe is connected to others, it's possible that these constants were shaped by interactions across the multiverse, creating a kind of cosmic harmony. This theory also has profound implications for cosmology. If quantum tunneling can create bridges between universes, it opens up the possibility that our universe isn't isolated. Instead, it might be part of a vast, interconnected network of realities, each influencing the others in ways we're only beginning to understand. And here's the kicker. If this is true, then the first quantum tunneling event wasn't just the beginning of our universe, it was the beginning of a multiverse. It's a staggering thought, one that challenges our understanding of reality itself. So, as we explore this theory, keep in mind that the multiverse isn't just science fiction. It's a serious scientific idea with the potential to reshape how we see the cosmos. And as we'll see, this is just one piece of a much larger puzzle. Now, let's shift our focus to a concept that lies at the very heart of quantum mechanics: zero-point energy. This is the idea that even in a perfect vacuum where you'd expect nothingness, there's still a tiny, persistent hum of energy. It's the lowest possible energy state, but it's far from empty. In fact, this energy might have played a crucial role in the very first quantum tunneling event, setting the stage for the universe's expansion. Here's the fascinating part. Zero-point energy isn't just a theoretical curiosity, it's a measurable phenomenon. Even in the absence of matter or light, quantum fields fluctuate, creating a kind of background energy that never disappears. These fluctuations are so small that they're often overlooked, but in the earliest moments of the universe, they could have been the spark that ignited everything. Imagine the universe before it was a universe, a seething, chaotic void filled with these tiny energy fluctuations. Under the right conditions, one of these fluctuations could have triggered a quantum tunneling event, allowing energy to escape from one state to another. This escape wouldn't just be a random occurrence, it could have been the catalyst for the universe's rapid expansion, what we now call cosmic inflation. Think of it like a pot of water on the verge of boiling. Even before bubbles form, tiny vibrations ripple through the water. In the same way, zero-point energy could have created the conditions for quantum tunneling, allowing the universe to bubble into existence. This idea suggests that the first quantum tunneling event wasn't just a random accident, it was a natural consequence of the universe's underlying energy. But why does this matter? For one, it gives us a potential explanation for how the universe could have expanded so quickly in its earliest moments. If zero-point energy provided the initial push, it could explain why the universe is so vast and uniform today. It also ties into the idea that even in the emptiest of spaces, there's always something happening, a reminder that the universe is far more dynamic than it appears. This theory also raises intriguing questions about the nature of reality. If zero-point energy can trigger quantum tunneling, could it still be influencing the universe today? Some scientists speculate that this energy might even play a role in dark energy, the mysterious force driving the universe's accelerated expansion. As we explore this idea, it's worth remembering that zero-point energy isn't just a theoretical concept. It's a real, measurable phenomenon that could hold the key to understanding the universe's origins. And as we'll see, this is just one piece of a much larger puzzle, one that continues to challenge and inspire scientists today. Now, let's dive into a concept that takes us even deeper into the quantum realm: quantum foam. Picture space-time not as a smooth, unbroken fabric, but as a turbulent, frothy sea at the tiniest scales imaginable. This is the essence of quantum foam, a chaotic and ever-changing landscape where the rules of classical physics break down and quantum mechanics takes the wheel. At these minuscule scales, space-time isn't stable, it's constantly fluctuating, bubbling with energy and creating tiny, fleeting structures. These fluctuations are so small that they're almost impossible to detect directly, but their effects could have been monumental in the early universe. In fact, quantum foam might have been the perfect environment for the first quantum tunneling event to occur. Here's how it works. Imagine space-time as a turbulent ocean, with waves and ripples constantly forming and collapsing. In this chaotic environment, particles and energy can pop in and out of existence, thanks to the uncertainty principle. Occasionally, these fluctuations could create just the right conditions for a quantum tunneling event, a moment where energy or particles jump from one state to another, bypassing the usual barriers. In the context of the early universe, this could have been the spark that ignited everything. A quantum tunneling event within the quantum foam might have allowed energy to escape from one state to another, triggering the rapid expansion we now call cosmic inflation. This idea suggests that the universe didn't just emerge from nothing. It emerged from a seething, dynamic quantum foam where the rules of reality were still being written. But what makes quantum foam so fascinating is its connection to the very fabric of space-time. According to some theories, these tiny fluctuations could be the building blocks of the universe itself. They might even hold clues about the nature of gravity and how it interacts with quantum mechanics, a puzzle that scientists are still trying to solve. This theory also raises intriguing questions about the nature of reality. If space-time is inherently frothy and turbulent at the smallest scales, what does that mean for our understanding of the universe? Could quantum foam still be influencing the cosmos today, shaping the way galaxies form and evolve? As we explore this idea, it's worth remembering that quantum foam isn't just a theoretical concept, it's a window into the deepest mysteries of the universe. It challenges us to rethink our assumptions about space, time, and the very nature of reality. And as we'll see, this is just one piece of a much larger puzzle, one that continues to inspire and perplex scientists to this day. Now, let's shift our focus to a theory that challenges our very perception of reality, the holographic principle. This mind-bending idea suggests that the universe we experience might not be what it seems. Instead of being a three-dimensional space filled with matter and energy, the holographic principle proposes that our universe could be a projection of information encoded on a two-dimensional surface. Think of it like a hologram where a flat image creates the illusion of depth and complexity. So how does this connect to the first quantum tunneling event? If the universe is essentially a projection of information, then quantum tunneling could be understood as a transfer of that information from one state to another. In this framework, the first quantum tunneling event might not have been a physical leap across space-time, but rather a shift in the underlying information that defines reality. Imagine the early universe as a vast, two-dimensional surface filled with encoded data. A quantum tunneling event could have been the moment when a piece of this information jumped from one configuration to another, triggering a cascade of changes that led to the birth of the universe as we know it. This idea aligns with the holographic principle's claim that all physical phenomena, including space, time, and matter, emerge from the interactions of this fundamental information. What's fascinating about this theory is its implications for higher dimensions. The holographic principle suggests that our three-dimensional universe might be a shadow or projection of a higher dimensional reality. In this context, the first quantum tunneling event could have been a transfer of information from this higher dimensional realm into our observable universe. This would mean that the origins of the cosmos are deeply tied to the flow of information across dimensions, a concept that bridges quantum mechanics and cosmology in a truly profound way. This theory also raises intriguing questions about the nature of existence. If the universe is a hologram, what does that mean for our understanding of reality? Are we, too, projections of information, living in a world that's fundamentally encoded on a cosmic surface? And if so, could quantum tunneling events still be happening today, subtly shaping the fabric of our reality? As we explore the holographic principle, it's clear that this theory offers a radical new perspective on the universe's origins. It challenges us to rethink not just how the universe began, but what it truly is. And as we'll see, this is just one of many theories that push the boundaries of our understanding, inviting us to imagine a cosmos far stranger and more interconnected than we ever thought possible. Now, let's turn our attention to a theory that ties the first quantum tunneling event to one of the most pivotal moments in the universe's history: cosmic inflation. This theory suggests that the rapid expansion of the early universe, known as inflation, might have been sparked by a quantum tunneling event. To understand this, let's first break down what cosmic inflation is. Cosmic inflation is the idea that, in the tiniest fraction of a second after the Big Bang, the universe underwent an exponential expansion, growing from the size of a subatomic particle to something far larger than our observable universe today. This rapid expansion helps explain why the universe appears so uniform on large scales and why it contains the structures we see, like galaxies and galaxy clusters. But what caused this sudden burst of growth? Here's where quantum tunneling comes into play. According to this theory, the first quantum tunneling event could have been the trigger for cosmic inflation. Imagine the early universe as a high-energy state, like a ball perched at the top of a hill. In this scenario, quantum tunneling would be the moment when the ball tunnels through the hill to a lower energy state, releasing a tremendous amount of energy in the process. This energy release could have set off the rapid expansion we call cosmic inflation. What's remarkable about this idea is how well it aligns with current cosmological models. Inflationary theory already provides a framework for understanding the universe's large-scale structure, and adding quantum tunneling as the trigger fits seamlessly into this picture. It suggests that the universe's expansion wasn't just a random event, but was instead driven by the fundamental laws of quantum mechanics. This theory also raises fascinating questions about the nature of the early universe. If quantum tunneling initiated inflation, what does that tell us about the conditions that existed before the Big Bang? Could there have been other quantum tunneling events that led to different universes, each with its own unique properties? These are the kinds of questions that keep cosmologists up at night as they try to piece together the story of our cosmic origins. As we explore the cosmic inflation trigger theory, it's clear that this idea offers a compelling link between quantum mechanics and the large-scale structure of the universe. It reminds us that even the most dramatic events in the cosmos might have their roots in the tiny, unpredictable world of quantum physics. And as we'll see, this is just one of many theories that continue to push the boundaries of our understanding, inviting us to imagine a universe that's far more dynamic and interconnected than we ever imagined. Now, let's venture into one of the most intriguing and mind-bending theories about the universe's first quantum tunneling event: the black hole singularity hypothesis. This theory takes us deep into the heart of a black hole, where the laws of physics as we know them break down and the unimaginable becomes possible. At the center of a black hole lies a singularity, a point of infinite density where gravity becomes so intense that not even light can escape. The conditions here are unlike anything else in the universe, with temperatures and pressures reaching levels that defy comprehension. It's in this extreme environment that some scientists believe the first quantum tunneling event could have occurred. Imagine the singularity as a place where space and time are so warped that the usual rules of physics no longer apply. In this chaotic realm, quantum fluctuations could become amplified, creating the perfect conditions for a tunneling event. Just as a particle can tunnel through an energy barrier in quantum mechanics, the singularity might have allowed a similar process on a cosmic scale. This event could have released an enormous amount of energy, potentially birthing an entirely new universe. What makes this idea so fascinating is its connection to the concept of a baby universe. Some theories suggest that a black hole singularity could act as a gateway, creating a new universe that exists independently of our own. In this scenario, the quantum tunneling event wouldn't just be a one-time occurrence. It could be the spark that ignites an entirely new cosmic reality. This theory also raises profound questions about the nature of black holes and their role in the cosmos. Could every black hole contain the seeds of a new universe? And if so, does that mean our own universe might have originated from a singularity in another reality? These are the kinds of questions that challenge our understanding of existence itself, blurring the lines between science and philosophy. As we explore the black hole singularity hypothesis, it's clear that this theory offers a bold and imaginative perspective on the origins of the universe. It reminds us that the cosmos is full of mysteries waiting to be unraveled, and that even the most extreme environments might hold the key to understanding our place in the grand tapestry of reality. With this theory, we're not just looking at the universe as it is, we're peering into the very fabric of creation itself, where the boundaries of space, time, and possibility are pushed to their limits. And as we'll see, this is just one of many ideas that continue to challenge and inspire us, inviting us to imagine a cosmos that's far more interconnected and dynamic than we ever thought possible. Now, let's shift our focus to another groundbreaking idea that ties the universe's first quantum tunneling event to the very fabric of space and time, the quantum gravity connection. This theory takes us into the realm of quantum gravity, where the familiar rules of general relativity and quantum mechanics collide, creating a framework that could explain how the first tunneling event unfolded. At the heart of this theory is the concept of space-time quantization. Unlike the smooth, continuous fabric described by Einstein's general relativity, quantum gravity suggests that space and time are made up of tiny, discrete units. Think of them as the pixels of the universe. Theories like loop quantum gravity propose that these fundamental building blocks of space-time could have played a crucial role in the first quantum tunneling event. Imagine the early universe as a seething, chaotic sea of these quantum space-time units. In such an environment, the boundaries between different states of reality might have been incredibly fluid. A quantum tunneling event could have occurred as a natural consequence of this instability, allowing the universe to transition from one state to another. This process wouldn't just be a random fluctuation. It would be a fundamental feature of how space-time behaves at the smallest scales. What's particularly fascinating about this idea is how it bridges the gap between the very large and the very small. Quantum gravity theories aim to unify the macroscopic world of galaxies and black holes with the microscopic world of particles and quantum fields. In doing so, they provide a potential explanation for how the first quantum tunneling event could have set the stage for the universe's expansion and evolution. This theory also raises intriguing questions about the nature of space-time itself. If space and time are quantized, does that mean there's a smallest possible unit of distance or duration? And if so, how does this affect our understanding of the universe's origins? These are the kinds of questions that push the boundaries of modern physics, challenging us to rethink our most fundamental assumptions about reality. As we explore the quantum gravity connection, it's clear that this theory offers a compelling perspective on the universe's first quantum tunneling event. It reminds us that the cosmos is not just a collection of stars and galaxies, it's a dynamic, interconnected system governed by laws that we're only beginning to understand. And as we'll see, this is just one piece of a much larger puzzle, inviting us to imagine a universe that's far more intricate and interconnected than we ever thought possible. With this theory, we're not just looking at the universe as it is, we're peering into the very foundation of reality itself, where the boundaries between space, time, and quantum mechanics blur into one. And as we continue our journey through these theories, we'll uncover even more insights into the mysteries of the cosmos, each one bringing us closer to understanding the true nature of existence. Now, let's turn our attention to a theory that connects the universe's first quantum tunneling event to one of the most enigmatic forces in the cosmos, dark energy. This mysterious force, which makes up about 68% of the universe's energy content, is responsible for the accelerated expansion of the universe. But could it also have played a role in the very first quantum tunneling event? The idea here is that dark energy, with its repulsive gravitational effect, might have created the conditions necessary for quantum tunneling to occur. In the early universe, when space and time were still in their infancy, dark energy could have acted as a catalyst, pushing the boundaries of reality just enough to allow a quantum tunneling event to take place. Think of it like a cosmic pressure, gently nudging the universe toward a state where such a transition was not only possible but inevitable. What makes this theory so intriguing is how it ties into our current understanding of cosmology. Dark energy is already a cornerstone of modern physics, explaining why the universe is expanding at an ever-increasing rate. If it also played a role in the first quantum tunneling event, it would mean that dark energy has been shaping the cosmos from the very beginning. This would provide a deeper connection between the universe's earliest moments and its present-day behavior, offering a unified explanation for both. But how exactly could dark energy have influenced quantum tunneling? One possibility is that it altered the energy landscape of the early universe, creating regions where the potential barriers between different quantum states were lower. In such an environment, a particle or field could more easily tunnel through these barriers, triggering the first quantum tunneling event. This process wouldn't just be a random occurrence, it would be a direct consequence of dark energy's influence on the fabric of reality. This theory also raises fascinating questions about the nature of dark energy itself. Is it a constant force, as some models suggest, or does it vary over time? And if it does change, how might that affect the likelihood of quantum tunneling events in the future? These are the kinds of questions that keep cosmologists up at night as they try to piece together the puzzle of the universe's origins and evolution. As we explore the dark energy catalyst theory, it's clear that this idea offers a fresh perspective on the universe's first quantum tunneling event. It reminds us that the forces shaping the cosmos today might have been at work from the very beginning, weaving a story that connects the past, present, and future of the universe. And as we'll see, this is just one more piece of the puzzle, inviting us to imagine a cosmos that's even more interconnected and dynamic than we ever thought possible. With this theory, we're not just looking at the universe as it is, we're peering into the very forces that have shaped it from the start, where the boundaries between energy, space, and quantum mechanics blur into one. And as we continue our journey through these theories, we'll uncover even more insights into the mysteries of the cosmos, each one bringing us closer to understanding the true nature of existence. Now, let's shift our focus to a theory that takes us into the realm of higher dimensions and vibrating strings, string theory. This groundbreaking framework in physics suggests that the fundamental building blocks of the universe aren't particles but tiny, vibrating strings. These strings exist in a space with more than the 3 dimensions we're familiar with, opening up a whole new way to understand the universe's first quantum tunneling event. According to string theory, the first quantum tunneling event could have been a transition between different states of reality, facilitated by the unique properties of these vibrating strings. Imagine the early universe as a vast, multidimensional landscape where strings vibrate at different frequencies, each corresponding to a different particle or force. In this scenario, quantum tunneling wouldn't just be a random jump. It would be a carefully orchestrated shift, guided by the interactions of these strings across multiple dimensions. One of the most fascinating aspects of this theory is how it ties quantum tunneling to the concept of extra dimensions. In string theory, these additional dimensions aren't just theoretical, they're essential for explaining how particles and forces behave. When a quantum tunneling event occurs, it could involve a string moving through these extra dimensions, effectively bridging the gap between two different states of reality. This process would be like a cosmic dance where the string's vibrations determine the outcome of the tunneling event. But what does this mean for the universe's origins? If string theory is correct, the first quantum tunneling event could have been a pivotal moment, setting the stage for the formation of matter, energy, and even space-time itself. The vibrations of these strings would have dictated the initial conditions of the universe, creating a delicate balance that allowed for the emergence of everything we see today. This theory also raises intriguing questions about the nature of reality. If quantum tunneling is a transition between different states, could there be other universes or realities connected to our own through these extra dimensions? And if so, how might they influence the evolution of our universe? These are the kinds of questions that string theory invites us to explore, offering a glimpse into a cosmos that's far more complex and interconnected than we ever imagined. As we delve into the string theory perspective, it's clear that this framework provides a rich and imaginative way to understand the universe's first quantum tunneling event. It challenges us to think beyond the limits of our three-dimensional world, inviting us to consider a reality where the boundaries between dimensions, particles, and forces blur into one. And as we continue our journey through these theories, we'll uncover even more insights into the mysteries of the cosmos, each one bringing us closer to understanding the true nature of existence. Now, let's turn our attention to a theory that connects the mysterious phenomenon of quantum entanglement to the universe's very first quantum tunneling event. Quantum entanglement is one of the most baffling and fascinating aspects of quantum mechanics. It describes how particles can become linked or entangled in such a way that the state of one particle instantly influences the state of another, no matter how far apart they are. This strange connection seems to defy our everyday understanding of space and time, and it might hold the key to understanding the early universe's structure. The quantum entanglement hypothesis suggests that entanglement could have played a crucial role in the first quantum tunneling event. Imagine the early universe as a dense, interconnected web of particles, all entangled with one another. In this scenario, quantum tunneling wouldn't just be an isolated event. It would be part of a larger, entangled network. When one particle tunnels through a barrier, its entangled partner could instantly respond, creating a ripple effect that influences the entire system. This interconnectedness could have provided the framework for the universe's first quantum tunneling event, linking the early universe's structure in ways we're only beginning to understand. One of the most intriguing aspects of this theory is how it ties quantum entanglement to the formation of the universe's large-scale structure. If particles in the early universe were entangled, their collective behavior could have set the stage for the first quantum tunneling event, which in turn could have influenced the distribution of matter and energy. This process might explain why the universe appears so uniform on large scales, with galaxies and cosmic structures forming in a seemingly coordinated way. In other words, entanglement could have been the cosmic glue that held the early universe together, guiding its evolution from the very beginning. But how does this fit into our understanding of quantum tunneling? If entanglement was present at the universe's birth, it could have acted as a kind of quantum communication channel, allowing particles to influence each other across vast distances. This would mean that the first quantum tunneling event wasn't just a random occurrence, it was part of a larger, interconnected process. The entangled particles could have worked together to create the conditions necessary for tunneling, ensuring that the event had a lasting impact on the universe's structure. This theory also raises profound questions about the nature of reality. If entanglement played a role in the first quantum tunneling event, could it still be influencing the universe today? And if so, how might this hidden connection shape the cosmos on both the smallest and largest scales? These are the kinds of questions that the quantum entanglement hypothesis invites us to explore, offering a new perspective on the universe's origins and its ongoing evolution. As we consider this theory, it's clear that quantum entanglement adds a fascinating layer to our understanding of the universe's first quantum tunneling event. It challenges us to think about the cosmos not as a collection of isolated particles, but as a deeply interconnected system where every event is part of a larger, entangled whole. And as we continue to explore these ideas, we'll uncover even more insights into the mysteries of the universe, each one bringing us closer to understanding the true nature of existence. Now, let's shift our focus to a theory that takes us into the realm of vacuum decay, a concept that might hold the key to understanding the universe's very first quantum tunneling event. The vacuum decay theory proposes that the early universe existed in a state known as a false vacuum, a temporary, unstable condition filled with potential energy. This false vacuum was like a stretched rubber band holding immense tension, waiting for the right moment to snap. And when it did, it triggered a quantum tunneling event that released an extraordinary amount of energy, setting the stage for the birth of the universe as we know it. To understand this theory, we need to dive into the idea of vacuum states. In quantum physics, a vacuum isn't just empty space, it's a state of minimal energy. But not all vacuums are created equal. A false vacuum is a higher energy state that appears stable but is actually teetering on the edge of collapse. Think of it like a ball perched on the top of a hill. It might stay there for a while, but the slightest nudge could send it rolling down into a lower, more stable position, the true vacuum. In the context of the early universe, this nudge could have been a quantum fluctuation, causing the false vacuum to decay into the true vacuum through a process of quantum tunneling. This transition wouldn't have been a quiet event. As the false vacuum decayed, it would have released an enormous amount of energy, creating a burst of activity that could have initiated the first quantum tunneling event. This energy release might have been the spark that set off the universe's expansion, filling it with the particles and forces that would eventually form stars, galaxies, and everything we see today. In this way, vacuum decay could have been the cosmic trigger that launched the universe into existence. One of the most fascinating aspects of this theory is how it connects quantum mechanics to the large-scale structure of the universe. If the first quantum tunneling event was caused by vacuum decay, it would explain why the universe appears so uniform on a cosmic scale. The rapid release of energy during the decay process would have smoothed out any irregularities, creating the even distribution of matter and energy we observe today. This idea aligns with what we see in the cosmic microwave background radiation, the faint afterglow of the Big Bang, which shows a remarkably consistent temperature across the universe. But the vacuum decay theory also raises some intriguing questions. For instance, could vacuum decay still be happening today? Some physicists speculate that our universe might still be in a false vacuum state, and a future decay event could have catastrophic consequences, effectively rewriting the laws of physics as we know them. While this might sound like science fiction, it's a reminder of how much we still have to learn about the nature of reality. As we explore this theory, it's clear that vacuum decay offers a compelling explanation for the universe's first quantum tunneling event. It paints a picture of a dynamic, ever-changing cosmos, where even the vacuum of space is filled with potential and possibility. And as we continue to investigate these ideas, we'll uncover even more about the forces that shaped the universe and the mysteries that still lie ahead. Now, let's journey back to the very beginning, the Planck epoch, a time so early in the universe's history that it's almost impossible to comprehend. This was the first fraction of a second after the Big Bang, a period when the universe was unimaginably hot, dense, and small. To put it into perspective, the entire cosmos was smaller than an atom, and the laws of physics as we know them today didn't yet apply. Instead, this was a realm where quantum mechanics and gravity were intertwined, creating conditions ripe for quantum tunneling events to shape the universe's destiny. The Planck epoch is named after Max Planck, the father of quantum theory, and it represents the earliest moment we can theorize about, a time when the universe was just 10 to the power of -43 seconds old. At this scale, space and time were not smooth and continuous, but instead existed in a chaotic, fluctuating state. Imagine a bubbling, frothy sea of energy where particles and forces flickered in and out of existence. It was within this turbulent environment that quantum tunneling events could have played a crucial role in setting the stage for everything that followed. Quantum tunneling, as we've discussed, allows particles to overcome barriers that would otherwise be impossible to cross. During the Planck epoch, these barriers were everywhere. The universe was so dense that even the fundamental forces, gravity, electromagnetism, and the strong and weak nuclear forces were unified into a single, all-encompassing force. This meant that particles and energy were constantly interacting in ways that defied our current understanding of physics. Quantum tunneling events could have allowed these particles to navigate this chaotic landscape, creating the first ripples of structure in the universe. One of the most intriguing ideas is that quantum tunneling might have been responsible for the initial separation of the fundamental forces. As the universe expanded and cooled, these forces began to differentiate, a process known as symmetry breaking. Quantum tunneling could have acted as the mechanism that triggered this separation, allowing the universe to transition from a state of perfect symmetry to the diverse and complex cosmos we see today. Without these early tunneling events, the universe might have remained a featureless, uniform soup of energy, never giving rise to the stars, galaxies, and planets we know. But the Planck epoch wasn't just a time of separation, it was also a time of creation. Quantum tunneling events could have generated the first fluctuations in energy density, tiny irregularities that would later grow into the large-scale structures of the universe. These fluctuations are what we see today in the cosmic microwave background radiation, the faint echo of the Big Bang. They are the seeds from which galaxies and galaxy clusters eventually formed, all thanks to the quantum processes that took place during the Planck epoch. Of course, studying this period is incredibly challenging. The energies involved were so extreme that our current theories of physics break down, and we can only speculate about what might have happened. But by combining insights from quantum mechanics, general relativity, and cosmology, scientists are beginning to piece together a picture of this mysterious era. The Planck epoch remains one of the most fascinating and elusive chapters in the story of the universe, a time when the rules were written and the stage was set for everything that followed. As we reflect on this theory, it's clear that the Planck epoch was a crucible of creation, a moment when the universe was both infinitely small and infinitely powerful. Quantum tunneling events, acting as the architects of this early cosmos, may have laid the groundwork for the universe's evolution, shaping the destiny of everything from the tiniest particles to the largest galaxies. And as we continue to explore these ideas, we'll uncover even more about the forces that shaped the universe and the mysteries that still lie ahead. Now, let's venture into a realm where science meets the profound mysteries of the mind, the quantum consciousness connection. This theory takes us beyond the physical and into the speculative, suggesting that consciousness itself, as a quantum phenomenon, might have played a pivotal role in the universe's first quantum tunneling event. It's a bold idea, one that bridges the gap between the cosmos and the human mind, proposing that our awareness of the universe could be deeply intertwined with its very creation. At the heart of this theory is the notion that consciousness isn't just a byproduct of the brain, but a fundamental aspect of reality, operating at the quantum level. Some scientists and philosophers argue that the strange, probabilistic nature of quantum mechanics, where particles exist in multiple states until observed, might be linked to the act of observation itself. In other words, consciousness could be the force that collapses quantum probabilities into definite outcomes. If this is true, then it's possible that consciousness, in some form, existed even at the universe's inception, influencing the first quantum tunneling events that set everything into motion. Imagine this during the Planck epoch, when the universe was a seething cauldron of energy and uncertainty. Quantum tunneling events were occurring constantly. But what if these events weren't purely random? What if they were guided in some way by a proto-consciousness, a fundamental awareness that permeated the fabric of reality? This idea suggests that the universe didn't just evolve blindly. Instead, it was shaped by a kind of cosmic consciousness, a force that nudged particles and energy into the configurations necessary for the universe to unfold as it did. This theory draws inspiration from the work of thinkers like Roger Penrose and Stuart Hameroff, who proposed the orchestrated objective reduction model, or ORCHOR. They suggest that quantum processes in the brain's microtubules could be the seat of consciousness, linking our minds to the quantum realm. Extending this idea to the early universe, it's possible that a similar quantum process could have influenced the first tunneling events, creating a feedback loop between the cosmos and consciousness. In this view, the universe isn't just a collection of particles and forces, it's a living, self-aware entity, constantly evolving through the interplay of quantum mechanics and consciousness. Of course, this theory is highly speculative and remains on the fringes of mainstream science. Critics argue that there's no direct evidence to support the idea that consciousness played a role in the early universe, and the mechanisms by which this could occur are still poorly understood. Yet, the quantum consciousness connection offers a tantalizing possibility that the universe and the mind are not separate but deeply connected, two sides of the same cosmic coin. It challenges us to rethink our place in the cosmos, suggesting that our awareness of the universe might be more than just a fleeting moment in its history. It could be an integral part of its very fabric. As we ponder this theory, it's worth considering the implications. If consciousness played a role in the first quantum tunneling event, then the universe might not be a cold, indifferent place but a dynamic, self-aware system. This idea blurs the line between the observer and the observed, suggesting that we are not just passive witnesses to the cosmos but active participants in its unfolding story. And while this theory remains speculative, it opens the door to a deeper understanding of the universe, one that embraces the mysteries of both the quantum realm and the human mind. With this thought-provoking idea in mind, let's turn our attention to another fascinating theory that explores the cyclical nature of the universe and how quantum tunneling might fit into its endless dance of creation and destruction. Now, shifting our gaze to the grand cosmic rhythm, we arrive at the cyclic universe model. This theory paints a picture of the universe not as a one-time event but as an eternal dance of expansion and contraction, a cycle that repeats endlessly across eons. Within this framework, the first quantum tunneling event takes on a new significance. It becomes the spark that ignites each new cycle, setting the stage for the universe to rise, fall, and rise again. At the heart of the cyclic model is the idea that the universe doesn't have a singular beginning or end. Instead, it undergoes a series of big bangs and big crunches, expanding outward until gravity pulls everything back into a dense, hot state, only to explode outward once more. Quantum tunneling, with its ability to allow particles to overcome seemingly insurmountable barriers, could be the mechanism that triggers each new expansion. Imagine the universe collapsing into an ultra-dense state where the laws of physics as we know them break down. In this chaotic environment, quantum tunneling could provide the necessary escape route, allowing energy and matter to burst forth and begin the cycle anew. This idea aligns with the concept of a bounce, where the universe rebounds from a collapse rather than starting from nothing. Quantum tunneling could be the force that facilitates this bounce, enabling the transition from contraction to expansion. Some theories suggest that during the collapse, quantum fluctuations, tiny, random variations in energy, could create pockets of instability. These fluctuations might then lead to tunneling events that release enough energy to kickstart the next cycle of expansion. In this way, quantum tunneling becomes the cosmic reset button, ensuring the universe's endless renewal. The cyclic model also offers a solution to one of the biggest mysteries in cosmology, the arrow of time. In our current universe, time flows in one direction from past to future. But in a cyclic universe, each cycle could reset the arrow of time, creating a new direction with each expansion. Quantum tunneling, as a process that defies classical notions of cause and effect, could play a key role in this reset, allowing the universe to forget its previous state and start fresh. Of course, the cyclic universe model is not without its challenges. Critics point out that the extreme conditions of a big crunch would likely destroy all structure, making it difficult to explain how information or patterns could carry over from one cycle to the next. Yet, proponents argue that quantum tunneling, with its probabilistic nature, could preserve certain quantum states, allowing a form of continuity between cycles. This idea opens the door to a universe that is both eternal and ever-changing, a cosmic tapestry woven from endless threads of creation and destruction. As we contemplate the cyclic universe model, we're reminded of the profound interconnectedness of all things. Quantum tunneling, often seen as a microscopic phenomenon, takes on a cosmic role in this theory, shaping the very fabric of reality across unimaginable spans of time. It's a reminder that the universe is not static but dynamic, a living entity that breathes in and out, expanding and contracting in an eternal rhythm. With this vision of a cyclical cosmos in mind, let's turn our attention to another intriguing theory that delves into the collapse of quantum fields and how it might have set the stage for the universe's first quantum tunneling event. Now let's dive into the quantum field collapse theory, a fascinating idea that explores how the collapse of a quantum field might have set the stage for the universe's first quantum tunneling event. Picture a quantum field as a vast, invisible ocean of energy, constantly fluctuating and filled with potential. In the early moments of the universe, this field could have been in a highly unstable state, teetering on the edge of collapse. When such a collapse occurs, it releases an enormous amount of energy, potentially triggering a quantum tunneling event that allows particles to leap across barriers they normally couldn't overcome. This theory suggests that the collapse of a quantum field could have been the catalyst for the creation of matter and energy in the early universe. Imagine the field as a stretched rubber band holding immense tension. When it finally snaps, the energy released could cause particles to tunnel through barriers, creating the conditions necessary for the universe to burst into existence. This process might explain how the first quantum tunneling event occurred, providing the initial spark that led to the formation of everything we see today. One of the most intriguing aspects of this theory is how it ties into the concept of symmetry breaking. In the early universe, quantum fields were likely in a state of perfect symmetry, where all forces and particles were indistinguishable. But as the field collapsed, this symmetry was broken, giving rise to the distinct forces and particles we observe today. Quantum tunneling could have played a crucial role in this process, allowing the universe to transition from a state of uniformity to one of diversity. Critics of the quantum field collapse theory often point out the challenges of modeling such an event. The extreme conditions of the early universe make it difficult to predict exactly how a quantum field would behave during a collapse. However, proponents argue that the probabilistic nature of quantum mechanics provides a framework for understanding how such an event could occur. By studying the behavior of quantum fields in high-energy environments, scientists hope to uncover clues about how the first quantum tunneling event might have unfolded. As we explore this theory, we're reminded of the delicate balance that governs the universe. The collapse of a quantum field, while seemingly chaotic, could have been the precise event needed to set the cosmos in motion. It's a reminder that even the smallest fluctuations in the quantum realm can have profound consequences, shaping the very fabric of reality. With this in mind, let's turn our attention to the supersymmetry hypothesis, a theory that offers another compelling perspective on how the first quantum tunneling event might have shaped the universe. Now, shifting our focus to the supersymmetry hypothesis, we enter a realm where the elegance of symmetry meets the chaos of the early universe. Supersymmetry, often referred to as SUSY, is a theoretical framework in particle physics that proposes a profound relationship between two fundamental classes of particles, bosons and fermions. According to this idea, every particle we know has a yet-to-be-discovered superpartner, a mirror image with different properties. This symmetry isn't just a mathematical curiosity. It could hold the key to understanding the universe's first quantum tunneling event. Imagine the early universe as a perfectly balanced scale, where bosons and fermions exist in perfect harmony. Supersymmetry suggests that this balance was eventually broken, a process known as symmetry breaking. When this happened, the universe underwent a dramatic transformation, and quantum tunneling could have played a pivotal role. As the symmetry broke, particles might have tunneled through energy barriers, creating the conditions necessary for the universe to evolve from a state of uniformity to one of complexity. One of the most compelling aspects of this hypothesis is how it ties into the concept of unification. Supersymmetry aims to bridge the gap between the four fundamental forces of nature: gravity, electromagnetism, and the strong and weak nuclear forces. In the early universe, these forces were likely unified, but as the symmetry broke, they separated, giving rise to the diverse interactions we observe today. Quantum tunneling could have been the mechanism that allowed this separation to occur, acting as a cosmic switch that set the universe on its current path. Critics of supersymmetry often point to the lack of experimental evidence for superpartners. Despite decades of searching, particle colliders like the Large Hadron Collider have yet to detect these elusive particles. However, proponents argue that the energy scales required to observe superpartners might be beyond our current technological capabilities. They also highlight how supersymmetry elegantly solves several outstanding problems in physics, such as the hierarchy problem, which questions why the Higgs boson is so much lighter than other particles. As we explore the supersymmetry hypothesis, we're reminded of the intricate dance between order and chaos in the cosmos. The breaking of symmetry, while seemingly disruptive, could have been the very process that allowed the universe to take shape. It's a testament to how even the most abstract ideas in physics can shed light on the origins of reality. With this in mind, let's turn our attention to the quantum wormhole theory, a concept that takes us even deeper into the mysteries of space-time and the universe's earliest moments. Now, let's venture into the intriguing realm of the quantum wormhole theory, where the fabric of space-time itself becomes a playground for the universe's earliest moments. Imagine a microscopic wormhole, a tunnel so tiny it exists at the quantum scale, yet powerful enough to bridge distant regions of space-time. This theory suggests that the first quantum tunneling event might have created such a wormhole, acting as a cosmic gateway that set the stage for the universe's expansion. At its core, a wormhole is a theoretical passage through space-time, often visualized as a shortcut between two points that would otherwise be impossibly far apart. In the context of the early universe, a quantum wormhole could have served as a conduit, allowing energy and particles to traverse regions that were once disconnected. This process might have been the spark that ignited the rapid expansion of the cosmos, transforming a dense, hot singularity into the vast, structured universe we observe today. One of the most fascinating aspects of this theory is how it ties into the concept of quantum tunneling. In quantum mechanics, particles can tunnel through barriers that would be insurmountable in classical physics. If a similar phenomenon occurred on a cosmic scale, it could have allowed the universe to transition from one state to another, effectively creating a bridge between different regions of space-time. This microscopic wormhole, born from quantum tunneling, might have been the catalyst for the universe's expansion, setting the cosmic clock in motion. The quantum wormhole theory also offers a unique perspective on the nature of space-time itself. If wormholes exist at the quantum level, they could provide a glimpse into the underlying structure of reality, revealing connections that are otherwise hidden from view. This idea aligns with broader theories in physics, such as string theory and quantum gravity, which suggest that space-time may not be as smooth and continuous as it appears, but rather a complex, interconnected web at the smallest scales. Critics of this theory often point to the lack of direct evidence for wormholes, as well as the immense challenges in detecting such microscopic phenomena. However, proponents argue that the extreme conditions of the early universe might have allowed for the formation of these quantum tunnels, even if they are no longer observable today. They also highlight how this theory could help explain some of the universe's most puzzling features, such as the uniformity of the cosmic microwave background radiation and the large-scale structure of galaxies. As we explore the quantum wormhole theory, we're reminded of the profound interconnectedness of the cosmos. The idea that a microscopic tunnel could have played a role in shaping the universe is both humbling and exhilarating. It challenges us to rethink our understanding of space, time, and the very fabric of reality. With this in mind, let's turn our attention to the quantum decoherence trigger, a concept that delves into how the loss of quantum coherence might have stabilized the early universe, paving the way for the structures we see today. Now, shifting our focus to the quantum decoherence trigger, we delve into a process that might have been crucial in stabilizing the early universe. Quantum decoherence refers to the phenomenon where quantum systems lose their coherence, transitioning from a state of superposition to a more classical, stable state. In the chaotic environment of the early universe, this process could have played a pivotal role in shaping the cosmos as we know it. Imagine the early universe as a turbulent sea of quantum fluctuations, where particles and energy existed in a state of constant uncertainty. In such a scenario, quantum decoherence would act like a calming force, causing these fluctuations to settle into more defined states. This stabilization could have been essential for the first quantum tunneling event, providing the necessary conditions for the universe to transition from a highly unstable state to one where structure and order could begin to emerge. One way to think about this is through the lens of quantum superposition. In a superposition state, particles exist in multiple states simultaneously, creating a complex and unpredictable environment. However, when decoherence occurs, these particles choose a single state, reducing the overall complexity and allowing for more predictable interactions. In the context of the early universe, this reduction in complexity might have been the key to initiating the first quantum tunneling event, enabling the universe to expand and evolve. The quantum decoherence trigger also offers insights into the uniformity of the cosmic microwave background radiation. If decoherence played a role in stabilizing the early universe, it could explain why the universe appears so uniform on large scales. By reducing the randomness of quantum fluctuations, decoherence might have smoothed out the initial irregularities, leading to the homogeneous universe we observe today. Critics of this theory often point to the challenges of directly observing quantum decoherence in the early universe. However, proponents argue that the extreme conditions of that time would have made decoherence a natural and inevitable process. They also highlight how this theory aligns with our understanding of quantum mechanics, providing a plausible explanation for the transition from quantum chaos to cosmic order. As we explore the quantum decoherence trigger, we gain a deeper appreciation for the delicate balance that allowed the universe to evolve from a state of quantum uncertainty to one of classical stability. This theory not only sheds light on the early moments of the cosmos, but also underscores the intricate interplay between quantum mechanics and the large-scale structure of the universe. With this understanding, let's now turn our attention to the quantum information theory, which explores how the transfer of information between quantum states might have been the foundation for the universe's formation. Now, let's venture into the fascinating realm of quantum information theory, a perspective that frames the first quantum tunneling event as a transfer of information between quantum states. This theory suggests that the universe's formation might have been driven not just by energy or matter, but by the flow of information itself. At its core, quantum information theory explores how information is encoded, processed, and transferred within quantum systems, offering a unique lens through which to view the birth of the cosmos. Picture the early universe as a vast, interconnected network of quantum states, each holding a piece of information. In this framework, the first quantum tunneling event could be seen as a critical moment when information was exchanged between these states, triggering a cascade of events that led to the universe's expansion. This idea aligns with the concept that information is a fundamental building block of reality, as fundamental as space, time, or energy. One way to understand this is by considering how quantum systems encode information. In quantum mechanics, particles can exist in multiple states simultaneously, a phenomenon known as superposition. When these particles interact, they exchange information which can influence their behavior and the overall system. In the context of the early universe, this exchange of information might have been the catalyst for the first quantum tunneling event, setting the stage for the universe to emerge from a state of quantum uncertainty. Quantum information theory also introduces the idea of entanglement, where particles become linked in such a way that the state of one instantly influences the state of another, no matter the distance. If entanglement played a role in the early universe, it could explain how information was rapidly transferred across vast regions, creating the conditions necessary for quantum tunneling. This interconnectedness might have been the glue that held the nascent universe together, allowing it to evolve in a coherent and structured manner. Critics of this theory often question how information transfer alone could lead to the creation of matter and energy. However, proponents argue that information is not just a passive record but an active participant in shaping reality. They point to experiments in quantum computing, where manipulating information at the quantum level can produce tangible effects, as evidence that information transfer could have profound consequences on a cosmic scale. The quantum information theory also offers a fresh perspective on the universe's fine-tuning. If information transfer was the driving force behind the first quantum tunneling event, it could explain why the universe appears so finely balanced. The precise exchange of information might have set the parameters for the laws of physics, ensuring the stability and complexity we observe today. As we explore this theory, we're reminded of the profound interconnectedness of all things in the universe. The idea that information transfer could have been the spark that ignited the cosmos challenges us to rethink our understanding of reality itself. It invites us to consider that the universe might be, at its heart, a vast network of information, constantly evolving and reshaping itself. With this in mind, let's now turn our attention to the quantum chaos hypothesis, which explores how chaotic quantum fluctuations in the early universe might have triggered the first quantum tunneling event, leading to the emergence of order from chaos. Now let's dive into the intriguing quantum chaos hypothesis, a theory that suggests the first quantum tunneling event might have been sparked by chaotic quantum fluctuations in the early universe. This idea flips the script on how we think about order and chaos, proposing that what seems random at the quantum level could have been the very force that brought structure to the cosmos. Imagine the early universe as a turbulent sea of quantum particles, each jostling and colliding in unpredictable ways. In this chaotic environment, tiny fluctuations in energy and matter could have created pockets of instability. These pockets, under the right conditions, might have triggered the first quantum tunneling event, allowing particles to overcome energy barriers they wouldn't normally be able to cross. This sudden shift could have set off a chain reaction, transforming chaos into the beginnings of order. The quantum chaos hypothesis draws inspiration from chaos theory, which studies how small changes in initial conditions can lead to vastly different outcomes. In the context of the early universe, even the tiniest quantum fluctuation could have had a ripple effect, amplifying over time to shape the universe's structure. This aligns with the idea that the universe didn't start as a perfectly ordered system, but rather emerged from a state of quantum turbulence. One of the most fascinating aspects of this theory is how it bridges the gap between chaos and order. While chaos often implies randomness, the quantum chaos hypothesis suggests that within that randomness lies the potential for structure. Think of it like a storm. While it may seem chaotic, the patterns of wind and rain follow underlying physical laws. Similarly, the chaotic quantum fluctuations in the early universe might have followed hidden rules that ultimately led to the formation of galaxies, stars, and planets. Critics of this theory often point out the difficulty in modeling such chaotic systems, especially when dealing with the extreme conditions of the early universe. However, advancements in quantum computing and simulations are beginning to shed light on how chaotic quantum behavior could lead to ordered outcomes. These tools allow scientists to explore scenarios where quantum chaos might have played a pivotal role in the universe's birth. The quantum chaos hypothesis also raises profound questions about the nature of reality. If chaos can give rise to order, does that mean randomness is an essential ingredient in the universe's recipe? And if so, how much of what we see around us is the result of chance versus necessity? These questions challenge us to rethink our understanding of the cosmos and our place within it. As we reflect on this theory, we're reminded that the universe is full of surprises. What might seem like chaos at one level could be the foundation of order at another. The quantum chaos hypothesis invites us to embrace the complexity of the cosmos and consider that even in the most turbulent moments, there's potential for something extraordinary to emerge. With this in mind, let's now explore the quantum time loop theory, which proposes that the first quantum tunneling event might have been facilitated by a loop in time, creating a self-sustaining universe. Now, let's turn our attention to the quantum time loop theory, a mind-bending idea that suggests the first quantum tunneling event could have been influenced by a loop in time itself. This theory challenges our conventional understanding of time as a linear progression, proposing instead that time might fold back on itself, creating a self-sustaining cycle that could have played a crucial role in the birth of the universe. Picture time not as a straight line but as a loop where the past, present, and future are interconnected. In this scenario, the first quantum tunneling event might have been a moment where time folded back on itself, allowing particles to traverse energy barriers in a way that wouldn't be possible in a purely linear timeline. This looping effect could have created a feedback mechanism where the tunneling event reinforced itself, leading to the formation of a stable, self-sustaining universe. The quantum time loop theory draws inspiration from concepts in theoretical physics, such as closed time-like curves, which describe paths through space-time that loop back to their starting point. While these ideas are often associated with science fiction, they have serious implications for our understanding of quantum mechanics and cosmology. If time can loop, it opens up the possibility that the universe's origins are not a one-time event but part of an ongoing cycle. One of the most intriguing aspects of this theory is how it addresses the question of causality. In a linear timeline, cause and effect follow a straightforward sequence, but in a time loop, cause and effect can become intertwined, creating a situation where the effect might influence the cause. This could mean that the first quantum tunneling event was both the cause and the result of the universe's creation, a paradox that challenges our fundamental notions of how reality works. Critics of the quantum time loop theory often point to the lack of empirical evidence for time loops and the difficulty in reconciling such ideas with our current understanding of physics. However, some researchers argue that the extreme conditions of the early universe might have allowed for phenomena that seem impossible under normal circumstances. As our tools for exploring quantum mechanics and spacetime continue to improve, we may find new ways to test these ideas. This theory also raises profound questions about the nature of existence. If the universe is self-sustaining through a time loop, does that mean it has always existed in some form? And if so, what does that imply about the future? These questions push the boundaries of our understanding and invite us to consider that the universe might be far more complex and interconnected than we ever imagined. As we explore the quantum time loop theory, we're reminded that the universe is full of mysteries waiting to be unraveled. The idea that time itself could loop back to facilitate the first quantum tunneling event is a testament to the creativity and ingenuity of scientific thought. It challenges us to think beyond the limits of our current knowledge and imagine possibilities that stretch the boundaries of reality. With this in mind, let's now shift our focus to the quantum phase transition, a theory that explores how a sudden shift in the quantum realm could have initiated the first quantum tunneling event, setting the stage for the universe's birth. Now let's dive into the quantum phase transition, a fascinating theory that compares the birth of the universe to something as familiar as water turning to ice. Just as water undergoes a dramatic shift when it freezes, the quantum realm might have experienced a similar transformation, triggering the first quantum tunneling event and setting the stage for the universe's creation. Imagine the early universe as a chaotic, high-energy state, much like boiling water. In this state, particles and energy are in constant motion with no clear structure or order. But as the universe began to cool, it reached a critical point, a phase transition where everything suddenly shifted. This transition could have been the moment when the first quantum tunneling event occurred, allowing particles to cross energy barriers that were previously insurmountable. This idea draws on the concept of phase transitions in physics, where a system undergoes a sudden change in its properties. For example, when water freezes, its molecules rearrange into a crystalline structure, creating ice. Similarly, during the universe's early moments, a phase transition in the quantum realm might have caused space-time itself to reorganize, creating the conditions necessary for quantum tunneling to take place. One of the key aspects of this theory is how it explains the emergence of order from chaos. In the high-energy state of the early universe, particles and energy were in a state of flux with no clear direction or purpose. But as the phase transition occurred, the universe began to stabilize, allowing for the formation of matter and energy in a more structured way. This shift could have been the catalyst for the first quantum tunneling event, which in turn led to the rapid expansion and evolution of the universe. The quantum phase transition theory also ties into our understanding of symmetry breaking, a process where a system loses its symmetry as it undergoes a phase change. In the early universe, this could have meant that the initial symmetry of the quantum field was broken, leading to the creation of distinct particles and forces. This breaking of symmetry might have been the driving force behind the first quantum tunneling event, setting the universe on its path to becoming the complex, structured cosmos we see today. Critics of this theory often point to the challenges of modeling such a phase transition in the quantum realm, given the extreme conditions of the early universe. However, researchers continue to explore this idea, using advanced mathematical models and simulations to better understand how such a transition could have occurred. As our tools and techniques improve, we may uncover new evidence that supports this intriguing theory. The quantum phase transition theory not only offers a compelling explanation for the first quantum tunneling event, but also invites us to think about the universe in a new way. It suggests that the birth of the cosmos might have been a moment of profound transformation, where chaos gave way to order and the universe as we know it began to take shape. With this in mind, let's now explore the quantum entropy hypothesis, a theory that examines how the concept of entropy or disorder might have played a role in the first quantum tunneling event and the creation of the universe. Now, shifting our focus to the quantum entropy hypothesis, we delve into the intriguing possibility that entropy, the measure of disorder in a system, played a pivotal role in the universe's first quantum tunneling event. This theory connects the dots between the chaotic nature of the early universe and the fundamental laws of thermodynamics, offering a fresh perspective on how the cosmos came into being. Entropy is often described as the tendency of systems to move from order to disorder over time. According to the second law of thermodynamics, entropy in an isolated system always increases, meaning that disorder naturally grows. But how does this relate to the birth of the universe? The quantum entropy hypothesis suggests that the first quantum tunneling event might have been driven by this very principle of increasing entropy. Picture the early universe as a highly ordered, low-entropy state, a pristine, almost perfect system. However, as the universe began to expand and cool, entropy started to rise. This increase in disorder could have created the conditions necessary for quantum tunneling to occur. In this scenario, the first quantum tunneling event might have been a natural response to the growing entropy, allowing particles to overcome energy barriers and initiate the processes that led to the formation of matter and energy. One of the most fascinating aspects of this theory is how it aligns with the second law of thermodynamics. While the law states that entropy increases over time, it doesn't specify how that increase manifests. In the context of the early universe, the rise in entropy could have triggered quantum tunneling, effectively acting as a mechanism to redistribute energy and matter in a way that allowed the universe to evolve. Critics of the quantum entropy hypothesis often question how such a process could occur in the extreme conditions of the early universe, where traditional notions of entropy might not apply. However, proponents argue that even in these extreme environments, the fundamental principles of thermodynamics could still hold, providing a framework for understanding the universe's origins. This theory also invites us to reconsider the role of disorder in the cosmos. While entropy is often associated with chaos, it can also be seen as a driving force for change and complexity. In the case of the early universe, the increase in entropy might have been the catalyst that allowed quantum tunneling to occur, setting the stage for the intricate structures and systems we observe today. As we continue to explore the mysteries of the universe, the quantum entropy hypothesis offers a compelling lens through which to view the first quantum tunneling event. It challenges us to think about the interplay between order and disorder and how these forces might have shaped the cosmos in its earliest moments. With this in mind, let's now turn our attention to the quantum resonance theory, which explores how the phenomenon of quantum resonance might have influenced the first quantum tunneling event and the formation of the universe. Now, let's tune into the quantum resonance theory, a fascinating idea that explores how the harmony of vibrating particles might have shaped the universe's first quantum tunneling event. Quantum resonance is a phenomenon where particles vibrate in sync, creating a kind of cosmic rhythm that can influence their behavior. This theory suggests that such resonance could have been a key player in the early universe, providing the stability needed for quantum tunneling to occur. Imagine the early universe as a vast, chaotic orchestra with particles buzzing around in all directions. Amid this chaos, certain particles might have begun vibrating in harmony, creating pockets of order. This synchronization could have allowed particles to overcome energy barriers more easily, facilitating the first quantum tunneling event. In essence, quantum resonance might have acted like a tuning fork, setting the stage for the universe to emerge from the void. One of the most intriguing aspects of this theory is how it connects the microscopic world of particles to the macroscopic structure of the universe. Just as musical notes can combine to create a symphony, the harmonious vibrations of particles could have laid the groundwork for the formation of matter and energy. This idea aligns with the concept of coherence in quantum mechanics, where particles behave in a unified way, leading to stable and predictable outcomes. Critics of the quantum resonance theory often point out the challenges of applying such a concept to the extreme conditions of the early universe. However, proponents argue that even in those chaotic moments, the principles of resonance could still apply, offering a mechanism for order to emerge from disorder. This perspective invites us to think about the universe not just as a collection of random events, but as a system where harmony and synchronization play a crucial role. The quantum resonance theory also raises questions about the nature of reality itself. If particles can vibrate in harmony to create stability, could this principle extend to other aspects of the cosmos? Some scientists speculate that resonance might be a fundamental force shaping everything from the smallest particles to the largest structures in the universe. This idea opens up new avenues for exploring how the universe operates on both the quantum and cosmic scales. As we consider the implications of this theory, it's clear that quantum resonance offers a unique lens through which to view the first quantum tunneling event. It challenges us to think about the universe as a dynamic, interconnected system where harmony and synchronization are not just byproducts, but essential components of its very existence. With this in mind, let's now shift our focus to the quantum duality connection, which examines how the wave-particle duality of quantum mechanics might have influenced the first quantum tunneling event and the structure of the universe. Now, let's explore the quantum duality connection, a theory that delves into one of the most mind-bending principles of quantum mechanics, wave-particle duality. This concept suggests that particles, such as electrons or photons, can behave both as particles and waves depending on how they are observed. But how does this strange duality tie into the universe's first quantum tunneling event? Let's break it down. In the early universe, particles existed in a state of extreme uncertainty, where their wave-like and particle-like behaviors were constantly in flux. Wave-particle duality tells us that particles don't have a fixed form until they are observed or interact with their environment. This means that in the chaotic moments following the Big Bang, particles could have oscillated between wave-like and particle-like states, creating a dynamic and unpredictable landscape. This duality might have played a crucial role in the first quantum tunneling event. Imagine a particle as a wave spreading out across space, exploring multiple paths simultaneously. In this wave-like state, the particle could have encountered an energy barrier, a point where classical physics would say it couldn't pass. But because of its wave nature, the particle could have tunneled through this barrier, effectively bypassing it. This tunneling phenomenon, driven by wave-particle duality, could have been the spark that set the universe in motion. What's even more fascinating is how this duality might have influenced the structure of the universe. Waves can interfere with each other, creating patterns of peaks and troughs. In the early universe, this interference could have led to regions of higher and lower energy density, laying the groundwork for the formation of galaxies and cosmic structures. In other words, the wave-like behavior of particles might have acted like a cosmic blueprint, shaping the universe on a grand scale. Critics of this theory often point out the difficulty of applying wave-particle duality to the extreme conditions of the early universe. However, proponents argue that the principles of quantum mechanics, including duality, are universal and would have applied even in those chaotic moments. This perspective suggests that the universe's structure isn't just a result of random chance, but a consequence of the fundamental behaviors of particles. The quantum duality connection also raises profound questions about the nature of reality. If particles can exist as both waves and particles, what does that say about the fabric of the universe? Some scientists speculate that this duality might hint at a deeper, underlying reality where the boundaries between waves and particles blur, offering a glimpse into the true nature of existence. As we reflect on this theory, it's clear that wave-particle duality offers a unique perspective on the first quantum tunneling event. It challenges us to think about the universe not just as a collection of particles, but as a dynamic interplay of waves and particles, where the very nature of reality is fluid and ever-changing. With this in mind, let's now turn our attention to the quantum probability wave, a theory that explores how the collapse of a quantum probability wave might have triggered the first quantum tunneling event, leading to the creation of the universe as we know it. Now, shifting our focus to the quantum probability wave, we dive into a theory that takes us to the very heart of quantum mechanics. This idea revolves around the concept of probability waves, which describe the likelihood of finding a particle in a particular state or location. In the quantum world, particles don't have definite positions until they are observed. Instead, they exist as a cloud of probabilities represented by these waves. But how does this relate to the universe's first quantum tunneling event? Let's explore. In the early moments of the universe, everything was in a state of quantum uncertainty. Particles weren't fixed in place but existed as probability waves spreading out across space and time. These waves represented all the possible states a particle could be in, from its position to its energy level. According to the quantum probability wave theory, the first quantum tunneling event might have been triggered by the collapse of one of these probability waves. Imagine a particle existing in a superposition of states, with its probability wave encompassing multiple possibilities. When this wave collapsed, perhaps due to an interaction or a fluctuation, it could have caused the particle to tunnel through an energy barrier, creating a ripple effect that set the universe in motion. This collapse of the probability wave isn't just a random event. It's governed by the rules of quantum mechanics, which dictate how and when a wave collapses into a definite state. In the context of the early universe, this collapse could have been the spark that initiated the first quantum tunneling event, leading to the creation of matter, energy, and the very fabric of space-time. It's a fascinating idea that suggests the universe's birth wasn't just a random explosion, but a carefully orchestrated event driven by the laws of quantum physics. Critics of this theory often question how a single probability wave collapse could have such a monumental impact. However, proponents argue that in the extreme conditions of the early universe, even the smallest quantum event could have had far-reaching consequences. The collapse of a probability wave could have acted like a domino effect, triggering a cascade of quantum tunneling events that shaped the universe's evolution. What's truly intriguing about this theory is how it connects the abstract world of quantum mechanics to the tangible reality we see today. The collapse of a probability wave isn't just a mathematical concept, it's a fundamental process that could have laid the foundation for everything we know. From the formation of galaxies to the structure of atoms, the quantum probability wave theory offers a compelling explanation for how the universe came into being. As we consider this theory, it's worth reflecting on the profound implications it has for our understanding of reality. If the universe began with the collapse of a probability wave, what does that say about the nature of existence? Some scientists speculate that this idea hints at a deeper, underlying order to the cosmos, where probability and certainty are intertwined in ways we're only beginning to understand. With this in mind, let's now turn our attention to the quantum singularity hypothesis, a theory that explores how a quantum singularity, a point of infinite density, might have caused the first quantum tunneling event, birthing the universe from a single point. Now, let's venture into the realm of the quantum singularity hypothesis, a theory that takes us to the very edge of what we understand about the universe's origins. This idea centers around the concept of a quantum singularity, a point of infinite density where the laws of physics as we know them break down. Imagine a single, unimaginably small point containing all the energy, matter, and potential of the entire universe. It's a mind-bending thought, but one that could hold the key to understanding the first quantum tunneling event. In the context of the early universe, a quantum singularity represents a state where space and time are compressed to an infinitely small scale. Under such extreme conditions, the rules of classical physics no longer apply and quantum mechanics takes over. Here, particles and energy exist in a state of pure potential, with no definite properties until they interact or collapse into a specific state. According to this hypothesis, the first quantum tunneling event could have occurred when this singularity reached a critical point, causing a particle or energy fluctuation to tunnel through an energy barrier. This event, though infinitesimally small, could have unleashed a cascade of quantum effects, leading to the rapid expansion and formation of the universe. But what makes a quantum singularity so unique? Unlike a black hole singularity, which is governed by gravity, a quantum singularity exists in a realm where quantum effects dominate. This means that particles aren't bound by the same constraints as in classical physics. Instead, they can exist in multiple states simultaneously, governed by probability rather than certainty. When the singularity reached a tipping point, it's possible that a quantum fluctuation caused a particle to tunnel through an energy barrier, effectively creating a bridge between the singularity and the nascent universe. This tunneling event could have been the spark that ignited the Big Bang, setting the stage for everything we see today. Critics of this theory often point to the challenges of studying such extreme conditions. After all, a quantum singularity exists at scales far beyond our current technological capabilities to observe or replicate. However, proponents argue that the mathematics of quantum mechanics and general relativity provide a framework for understanding how such an event could occur. The interplay between quantum fluctuations and the extreme density of the singularity creates a scenario where tunneling becomes not just possible but inevitable. What's particularly fascinating about the quantum singularity hypothesis is how it bridges the gap between the infinitely small and the infinitely large. A single quantum event at the heart of a singularity could have set off a chain reaction that shaped the entire cosmos. From the formation of galaxies to the structure of atoms, this theory suggests that the universe's complexity emerged from the simplest of beginnings, a single point of infinite potential. As we reflect on this idea, it's worth considering the profound implications it has for our understanding of existence. If the universe began as a quantum singularity, what does that say about the nature of reality? Some scientists speculate that this hypothesis hints at a deeper connection between the quantum world and the cosmos, where the smallest events can have the largest consequences. With this in mind, let's now explore the quantum entanglement network, a theory that suggests the early universe was a vast web of interconnected particles, all influencing each other in ways that could have facilitated the first quantum tunneling event. Now, let's shift our focus to the quantum entanglement network, a theory that paints a picture of the early universe as a vast, interconnected web of particles. Imagine billions of particles, each linked to one another through the mysterious phenomenon of quantum entanglement. This theory suggests that this intricate network could have played a crucial role in the first quantum tunneling event, setting the stage for the universe's birth. Quantum entanglement is one of the most fascinating aspects of quantum mechanics. It's the idea that particles can become so deeply connected that the state of one instantly influences the state of another, no matter how far apart they are. In the early universe, this entanglement could have created a cosmic web, where particles weren't just isolated entities but part of a larger, unified system. This interconnectedness might have allowed energy and information to flow seamlessly across the universe, creating the perfect conditions for quantum tunneling to occur. Here's how it could have worked. In the dense, chaotic environment of the early universe, particles were constantly interacting and entangling with one another. As these entangled particles fluctuated, they could have collectively overcome energy barriers that would have been impossible for a single particle to breach on its own. Think of it like a group of climbers working together to scale a mountain, each one supporting the others, making the impossible possible. In this case, the mountain is the energy barrier, and the climbers are the entangled particles, working in unison to facilitate the first quantum tunneling event. This theory also offers an intriguing explanation for the uniformity we observe in the universe today. The cosmic microwave background radiation, which is essentially a snapshot of the early universe, shows an astonishing level of consistency across vast distances. How could regions of the universe that were too far apart to have ever been in contact with each other share such similar properties? The quantum entanglement network suggests that these regions were once connected through a web of entangled particles, allowing information and energy to be shared instantaneously, even before the universe began to expand. But what makes this theory particularly compelling is its potential to bridge the gap between quantum mechanics and cosmology. Quantum entanglement is a well-documented phenomenon in the lab, but applying it to the scale of the entire universe opens up new possibilities for understanding the cosmos. If the early universe was indeed a network of entangled particles, it could explain not only the first quantum tunneling event, but also the large-scale structure of the universe we see today. Galaxies, clusters, and even the cosmic web itself might be the remnants of this primordial entanglement. Of course, like all theories about the universe's origins, the quantum entanglement network has its challenges. For one, we still don't fully understand how entanglement works on such a massive scale. Additionally, the extreme conditions of the early universe make it difficult to test this idea directly. However, advancements in quantum computing and simulations are beginning to shed light on how entanglement might operate in these environments, offering hope that we could one day validate this theory. As we ponder the implications of this idea, it's worth considering how it changes our understanding of the universe's beginnings. If the first quantum tunneling event was facilitated by a network of entangled particles, it suggests that the universe was born not from chaos, but from a deeply interconnected system. This interconnectedness might even extend to the present day, hinting at a universe that is far more unified than we ever imagined. With this in mind, let's now turn our attention to the quantum observer effect, a theory that explores the role of observation in the creation of the universe. Could the act of observing have influenced the first quantum tunneling event? Let's find out. Now, let's venture into one of the most intriguing and speculative theories of all, the quantum observer effect. This idea takes us into the heart of quantum mechanics, where the act of observation itself plays a pivotal role in shaping reality. Could it be that the first quantum tunneling event, the very spark that ignited the universe, was influenced by an observer? Let's dive into this fascinating possibility. At the core of quantum mechanics lies a strange and counterintuitive principle. Particles don't have definite properties until they are observed. This is famously illustrated by the double-slit experiment, where particles behave like waves until someone measures them, at which point they collapse into a definite state. The quantum observer effect takes this idea to its ultimate extreme, suggesting that the universe itself might have been observed into existence. In other words, the first quantum tunneling event could have been triggered by an act of observation, setting the stage for everything that followed. But who or what could have been the observer in the early universe? This is where the theory becomes truly speculative. Some propose that the observer might have been a conscious entity, perhaps even a form of proto-consciousness inherent in the fabric of reality itself. Others suggest that the observer could have been a quantum system within the universe, creating a self-referential loop where the universe observes itself into being. While these ideas might sound like science fiction, they raise profound questions about the nature of reality and the role of consciousness in the cosmos. One of the most compelling aspects of this theory is how it bridges the gap between quantum mechanics and philosophy. If the universe was indeed observed into existence, it implies that consciousness and reality are deeply intertwined. This idea echoes ancient philosophical concepts, such as the notion that the mind and the universe are inseparable. It also challenges our understanding of causality, suggesting that the act of observation might not just reveal reality but actively shape it. Of course, the quantum observer effect is not without its critics. Many scientists argue that applying the principles of quantum mechanics to the entire universe is a stretch, especially when it comes to the role of consciousness. After all, quantum observation in the lab typically involves precise measurements by instruments, not conscious beings. Additionally, the extreme conditions of the early universe make it difficult to test this theory directly. However, some researchers are exploring ways to simulate these conditions using advanced quantum computers, offering a glimmer of hope for future validation. Despite the challenges, the quantum observer effect remains a captivating idea that pushes the boundaries of our understanding. It invites us to consider the possibility that the universe is not just a collection of particles and forces, but a dynamic, participatory reality shaped by observation. Whether or not this theory holds up to scientific scrutiny, it encourages us to rethink our place in the cosmos and the profound connection between the observer and the observed. As we wrap up our exploration of the quantum observer effect, we're left with a tantalizing question. Could the universe itself be the ultimate observer, constantly shaping and reshaping reality through the act of observation? This idea brings us full circle, connecting the mysteries of quantum mechanics to the grand tapestry of the cosmos. And with that, we've reached the end of our journey through 30 theories about the universe's first quantum tunneling event. Each theory offers a unique lens through which to view the origins of everything, reminding us that the universe is far more mysterious and interconnected than we ever imagined. As we bring our exploration to a close, it's remarkable to reflect on the sheer diversity of ideas surrounding the universe's first quantum tunneling event. From the Big Bang quantum fluctuation to the quantum observer effect, each theory offers a unique perspective on how the cosmos might have begun. Some theories, like the multiverse connection and the holographic principle, stretch our imagination by suggesting that our universe is just one piece of a much larger puzzle. Others, such as the zero-point energy hypothesis and the quantum foam theory, dive deep into the quantum realm, revealing how the tiniest scales of existence could hold the key to the universe's origins. And then there are the more speculative ideas, like the quantum consciousness connection and the quantum observer effect, which challenge us to consider the role of consciousness itself in shaping reality. What's truly fascinating is how these theories, though often wildly different, all point to one undeniable truth: the universe is far more mysterious and interconnected than we ever imagined. Whether it's through the lens of quantum gravity, string theory, or even the cyclic universe model, each idea invites us to rethink our understanding of existence. They remind us that the questions we ask about the cosmos are just as important as the answers we seek. And while many of these theories remain untested or even untestable for now, they inspire us to keep exploring, questioning, and pushing the boundaries of what we know. So, what do you think? Could the universe have begun with a single quantum tunneling event? Or is the truth even more extraordinary than we've imagined? Share your thoughts in the comments below. We'd love to hear your perspective on these mind-bending ideas. And if you're as captivated by the mysteries of the cosmos as we are, don't forget to like this video, subscribe to the channel, and hit the notification bell so you never miss an exploration into the wonders of the universe. Until next time, keep looking up and wondering, because the cosmos is full of secrets just waiting to be uncovered.